So how can we prepare an ester? Well, one way, it's not a very good way, is we can add a strong base to the carboxylic acid and then add a methyl iodide and do an SN2 on that alkyl group. Methyl iodide is something you have to be very careful of when you're working with because it's a strong alkylating agent. So if you spill it, get it on you, you're going to alkylate yourself. You don't want to do that, so be very careful with it. The better way to form them is with a Fischer esterification, where we take an alcohol, we take some acid, strong acid, sulfuric and phosphoric, and react them together, and we take a carboxylic acid and we can turn that into the ester. Now to do this, this oxygen of the ester of the alcohol ends up being this oxygen of the ester as we go along. Okay, if we had it labeled with an oxygen 18. So we can track that, which helps to explain what can happen in the mechanisms as we're going along. So here we have the mechanism for it, and in the mechanism it shows why the oxygen that adds from the alcohol ends up being the ester oxygen. So in this, we don't have a good nucleophile, so the first thing we have to do, just like in the last section, is we have to protonate the carbonyl. As we protonate the carbonyl, we turn the carboxylic acid into a great electrophile, so then our weak nucleophile methanol, or whatever alcohol, it doesn't even have to be methanol, adds in, breaks the carbon-oxygen double bond, forming the tetrahedral intermediate. We can remove the extra hydrogen off of that methanol we added in by another equivalent of methanol, grabbing it off to neutralize it, and then we can protonate one of the other OHs, or one of the other oxygens, and all of this is happening in equilibrium. So it's all going back and forth, but if you protonate the oxygen of the methyl OMe and kick it back off, you're just going back towards the starting material, so it doesn't get anywhere. So all of this is happening. You just have to be careful that you push it, get the mechanism to where you want it to go. And we all know Le Chatelier's principle forces it. We can make changes in the equilibrium by changing things and force it to go one way or the other. So we protonate the OH to make it a good leaving group, and then we can reform a carbonyl, kicking out that good leaving group we just formed, and then remove the extra hydrogen off of the carbonyl, and we get to our methyl ester. And the oxygen of the methanol ends up being this oxygen right here, because it is what adds into the carbonyl. So we have to be careful where things are as we're going along. So how can we make esters other ways? We can use an acid chloride. As we showed earlier, we can add an alcohol into the acid chloride to form the tetrahedral intermediate, reform the carbonyl, kick off the chlorine, and then take off our extra hydrogen with our pyridine to give us the ester. Okay. What else can we do with an ester? We can add hydroxide to make, followed by acid to make a carboxylic acid. We can, in this, if we have a labeled 18 oxygen on our ester, we can track where it shows up, and it ends up going off into the alcohol that's kicked off in the reaction. Okay, and we can show that by what we have in the mechanism here. Okay, so hydroxide can add into the carbonyl, break the CO double bond, form the tetrahedral intermediate, reform the carbonyl, kicking off our OR. So if this oxygen is labeled as an oxygen 18, we just kicked it off of the molecule, and now it's floating around where it can grab a hydrogen off of the carboxylic acid we just formed to get to the carboxylate. And that's the end of the first step, because we have base around. We have to get all the way to something that's stable in that solution. Then we can add acid to the solution, work it up, and we form the carboxylic acid. Okay, so this is a base catalyzed way to cleave an ester. We can also do it acid catalyzed, where we can add H3O plus hydronium ion to our whatever ester we have, and we get the carboxylic acid out of it. Okay, now this mechanism is a lot longer than the base catalyzed one, so you have to be careful what type of mechanism are you showing and what do you want to get out. So in an acid catalyzed mechanism, just like with aldehydes and ketones, our favorite section, the test we just took, the carbonyl goes and grabs a hydrogen off of the hydronium to make the carbonyl a better electrophile. So then our weak nucleophile water can add to it, breaking the CO double bond to form the tetrahedral intermediate. We can remove the extra hydrogen to form the neutral tetrahedral intermediate. We can protonate one of the other oxygens. You know, all of this, as I said in the last section, or the last mechanism, all of this is in equilibrium. It's all happening at the same time and going back and forth. We changed what happens in the overall equilibrium by changing conditions of the reaction. So we add more water, we're going to force it to go to the carboxylic acid. If we took the carboxylic acid and added more alcohol and acid, we'd force it to go to the ester. So we protonate our OR, because that's the one we want to get rid of, use an OH to reform the carbon-oxygen double bond, kicking off the leaving group, and then we can remove the extra hydrogen off of this to get to our neutral carboxylic acid. And it's just like the mechanism we just drew, cleaving the ester. It's just going the opposite direction. We just have to remember that in acid, we keep track of always protonating it first and deprotonating it last, and making sure we don't show anything other than the conjugate base of our acid with a negative charge on it. Okay, because we're in acid, we can't have strong bases formed, so we have to be very careful about that. So what else can we do with an ester? We can turn it into an amide, and by that we can just add an amine, a primary. We can add ammonia, a primary amine, a secondary amine, and we can force it to make the amide out of it. We can also reduce an ester with LAH, just like we did before. Add a hydride in, form the tetrahedral intermediate, reform the carbonyl, kicking off the leaving group, and then add a second equivalent of hydride, and we're at the alkoxide. And yes, I know there are two hydrogens on there. We don't have to draw those in. We know they're there, but you can draw them in if it helps. And then we add our acid or water solution in the end to kill off the reaction and form our alcohol. So that's the mechanism. It's the same mechanism we drew before for all of these. You know, if you're adding a really strong nucleophile, you add it in, kick off the leaving group, and then add it a second time, since we have the good leaving group on there. If we didn't have a good leaving group, we could only do it once, like when we reduced an aldehyde or a ketone. So we can also, with dibol, reduce an ester under careful conditions down to an aldehyde by only reducing it once. And dibol is diisobutyl aluminum hydride. We talked about it at the last test section, test 3. Okay. It's a weaker reducing agent than LAH, so it only reduces it down to the aldehyde, along with the lithium tri-T-butoxy aluminum hydride. Also only reduces it down to the aldehyde. What else can we do? We can add a Grignard to it, and in the mechanism, just like we showed on the last page with the LAH reducing the ester, the Grignard anion can add to the carbonyl, break the double bond. We can reform the carbonyl, kicking off the leaving group. Then we can add the second equivalent of Grignard to form the alkoxide, and then we can protonate it with our acidic water or water that we work up the reaction with in the end. And we get the tertiary alcohol. So remember what we said about the reactivity of all of these. The acid chloride is the most, the amide is the least. So the amide, once we have an amide, there's less we can do with an amide than all the others. Okay, so the most efficient way to form an amide is from the corresponding acid chloride as shown here. By now you can draw the mechanism for this, but we will obviously show it on the next page. The amine adds to the carbonyl, breaks the CO double bond, forming the tetrahedral intermediate. We reform the carbonyl, kicking off the leaving group, and then our neutral ammonia, whatever amine we're using, methylamine, dimethylamine, as long as there's a hydrogen on our amine. So we can't use the tertiary amine here, but a primary or secondary amine or ammonia works just fine. And we can remove the extra hydrogen and we get to the amide. Now what can we do with an amide? We can acid catalyzed hydrolysis the carboxylic acid, of which the mechanism, as I unfortunately flashed to the next screen, is it too. We can draw, and it's very similar to all the other acid catalyzed mechanisms we've shown. The first thing we do is protonate it because we're in acid. We have to make our electrophile better because we don't have a good nucleophile. Then water can add in, break the CO double bond to form the protonated tetrahedral intermediate. Then we can remove the extra hydrogen off of it to form the neutral tetrahedral intermediate. We can protonate the nitrogen. Now remember, only one positive charge on a small organic molecule at once. Protonate the amine, and then we can reform the carbonyl, kicking out our amine because we made a good leaving group. And then the amine, which became the best base we have in solution, grabs our extra hydrogen to give us the carboxylic acid. Okay, the exact same mechanism basically that we drew for the acid catalyzed cleavage of an ester, or the acid catalyzed turning a carboxylic acid into an ester. They're all basically the same mechanism. What else can we do with an amide? We can cleave it with base, followed by an acid workup, and in the base catalyzed way, we add in hydroxide, form the tetrahedral intermediate, reform the carbonyl, kicking out the amide, and then amidine, and then the amidine can go grab a hydrogen off of the carboxylic acid we just formed. Because we're in base, we're not going to have the carboxylic acid last, and that forms the carboxylate. And then in the workup, the carboxylate could go grab a hydrogen from the acid to form our carboxylic acid. Okay. Same base catalyzed mechanism. We see the difference between a base catalyzed and an acid catalyzed mechanism, and you know what that means on the test. The test is going to have an acid catalyzed mechanism because acid catalyzed mechanisms are cool. So you have to be careful that you know all of the proton transfers that have to happen as you're going along with that. Amides can also be reduced with LAH, and what we get when we reduce it, we don't kick the nitrogen off like we did with the carboxylic acid. When we reduced it, so with the reduction of an amine, we reduce it down to, or the reduction of an amide, we reduce it down to an amine. Okay, so we end up removing the carbon-oxygen double bond, add an H minus in, form an O minus. That's going to react with the aluminum, and then we can kick that out and then add another H minus. Okay, just like what we drew before with the carboxylic acid. Mostly all you need to know is you reduce the amide to the